Good morning, here we are. Once again, it's the video lecture, Physics 105B, video lecture 9. And we ended last time with the Taylor expansion, the multivariable Taylor expansion. So I'm going to review that and then we'll continue on characterizing extrema and that type of thing. And then the goal is to go back and understand and study in depth the small oscillations theory. So we needed the multivariable Taylor expansion, and experience shows that the students don't really know the thing, even though a textbook will just assume that you've seen it before. So we're spending our time understanding the multivariable Taylor expansion. It's worth it. And what we found here, what was right, Taylor and x1 to xn, and we have a scalar function of this vector variable. Then we have f of x is equal to f of x of 0 plus, so this is our first derivative term. It's the sum of first derivatives, partials, x of I evaluated at x sub 0, x sub I minus x sub 0 I equals 1 to n. And then the next term, and we're only going to take it to the quadratic term. I'll say a little more about this. A half. Now you have a double sum, j and k, second partial with respect to x, let's name them I and j, huh? I and j, xi, xj, evaluated at x sub 0, x sub I minus x0 I, x sub j minus x0 j. Good. And if you wanted to, and I showed it in my derivation last time, if you wanted the third order terms, you'd have a triple sum here, I, j, k, and so forth, third derivatives. So this can really be internalized as a basic bookkeeping. And so right under here, I'm putting the single variable. And we're going to keep doing this comparison we had last time. This is just f prime of x0, x minus x0. And this is just the 1/2 f double prime, x minus x0 squared, and so on. So let's have a look at this again. You know, in the single variable Taylor expansion, we had a point. We then had a straight line. If you just took these first terms here, this would be a straight line. The equation of a straight line, that would be your intercept, so to speak. Okay. This itself, x minus x0 squared, would just be a parabolic term, quadratic term. You're adding it to this straight line, and so forth with the higher order terms, the way we studied them last semester. You know, so that's a way of looking at things that should be completely transparent. I'm doing the one-dimensional version. So you've got y equals f of x, and your first thing, you've got an f of x0. There's your x0. There's your f of x0. Then you add f prime of x0 times x minus x0. You're describing a straight line. If you add to it these quadratic terms, suppose they are negative. Suppose they're negative, you'd be adding a parabola to this, right? The up facing down, and the upshot is, we'll do a third color here, that you're looking at a function. Since we'd be subtracting this off here, you're looking at something that goes like so. And we're interested in this because we're interested in approximating, so around a neighborhood of x0, we've got that point slope formula, and if we want a better approximation, we're adding this next term. Okay. Good. So the same thing is going on right here, except that we're in n space, or you could say first of all we're in 3 space to visualize it, or in n space, and then the chain rule tells us that we have to have this sum of derivatives, but this is still a first derivative term, okay? And this double sum here, this is a quadratic form. It's the generalization of this term right here for n variables. And now this point about what I call bookkeeping, you know, I goes from 1 to n derivative with respect to x sub I times that little increment with respect to x sub I. And here, it's just as easy. I and j go from 1 to n, so you've just got 1, 1, ij, etc., etc. So I think one of the last things I did last time was to discuss just that point. We could simplify the quadratic form even more. So suppose we just had our local or our point of interest at the origin. Then we wouldn't have to have these differences. We would just have those terms. So the second order terms. Okay. So we're going to look at this double sum, and let's go ahead and define this d squared f dxi dxj evaluated at x sub 0. We'll just call it f sub ij and leave off any other subscripts, okay? This is what we understand by that. Then our quadratic form, got the half sum over I equals 1 to n, j equals 1 to n. F sub ij, right? That's clearly just an n by n matrix. And let's also let x sub I minus x sub I0, we'll just give that a new name. H sub ij. I'm sorry, h sub I. H sub I. So f ij, and then we would have an h sub I, h sub j. That's a quadratic form, and we want, and the value or the properties of this matrix determine whether something's a local maximum, minimum, etc. Okay. So we have to be able to evaluate, analyze this matrix f sub ij. Matrix Fij is called the Hessian matrix, and it's the matrix of second derivatives, and we're going to use it to characterize extrema. So we've got this definition, and then local extrema. Okay. We have local minimum if Fij is what's called positive definite. Is positive definite. So what is positive definite? So this matrix is positive definite if any values of these vectors here always give you a positive number. Okay. Doesn't matter what these hi and hj are, you always get a positive number. Right? In other words, this second derivative term is positive for any x. Okay? And that makes sense, right? Then you've got a local minimum, because around that minimum, as we'd see in 3 dimensions, you know, your function is a bowl or something. It's got a valley, and around that local minimum there, x sub 0, y sub 0, any excursion from there gives you a larger value. So if there's a local minimum, this term has to be either positive or 0. So yeah, that's a technical term to make sure you have in your notes. You look up what positive definite means. There is a criterion for it that I'll just put down without proof. Go ahead and erase this. So this matrix Fij is positive definite if all determinants these are a certain form of subdeterminant. Let's see what the best way to put that is. Of the form F11, F1J, Fj1, Fjj are greater than 0. So what that means is you take, for your matrix, F11 to F1n, Fn1, Fnn, right? That would be your n by n determinant. These here, oh, I didn't write down. J equals 1 to n. So that's all of these corner determinants. So if j is equal to 1, it would just be this number. If j is equal to 2, it would be the 2 by 2 determinant. And if j is equal to n, it would be the n by n determinant. So if all of those are greater than 0, then this form here, this quadratic form, is positive definite. And we need that in order for our expansion to be around a local minimum. However, in mechanics, it's not going to be that bad. And we're not going to actually have to do a lot of this. It's just for the record, because generally we construct our problem and we see, you know, we locate the local minimum in advance, so to speak, by construction. We'll know that we're at a local minimum, okay, of the potential energy. So let me add a couple things here to make this complete. Second order terms. Yeah, and then we have to talk about what is a critical point, and that's the standard first derivative criterion. That one's not so fancy. So the first order terms in our expansion, in our Taylor expansion, critical points. So df dx of I at x sub 0 equals 0 for all I. Okay. I equals 1 to n. In other words, it's the first derivative criterion, but it has to hold for every one of your variables, and then you've got a critical point. So that we can have local max and local min. let me give some basic examples that we can visualize for starters. So I could use x and y or x1 and x2. I'll use x1 and x2. So functions of two variables, x1 and x2. And f of x1, x2 is equal to some constant plus x1 squared plus x2 squared. Okay, let's keep it simple. What is that? That's some kind of paraboloid, because in x1 and in x2, okay, your constant here, right, and good luck drawing it. And critical points are clearly at the origin. So df dx1 is equal to 2x1, partial f with respect to x2 is equal to 2x2. You know, let's make this a little more interesting while we can. Let's go ahead and put a letter A and a letter B here. This will make it more general. So we have 2a x1, 2b x2. And then d squared f dxi dxj. Let's go ahead and write it as a 2 by 2 matrix. So with respect to x1, we're going to have a 2a. With respect to x2, we're going to have 2b, and then the mixed derivatives, of course, vanish. D squared dx f dx1 dx2 vanishes, and that does as well. So this is great now, because suppose a and b are both positive, then we have a local minimum. Okay. What if a is greater than 0 but b is less than 0? Then we have a saddle. So I'm going to put these down as notes so that we can go back to that. Note a, b, both greater than 0, then we have a local minimum at 0, 0. Okay. A greater than 0, B less than 0. It's a saddle. And of course, this criterion here is not fulfilled because the first corner determinant would just be a, 2a, but the second would be positive, but the second would be 2a times 2b would minus 4a, or 4ab, where b is negative, so it'd be negative. So we have a saddle, and note Fij is not positive definite. Now, if A and B are both negative, then we have an inverted bowl. We have a hill. We have a hill and we have a local maximum. Good. So with a very simple example, you can see through this really clearly. The higher the dimension, the more rich and complicated the thing could be, and you would no longer just be able to look at your matrix and know whether it's positive, definite, or not. With the 2 by 2 matrix, in fact, with the full 2 by 2 matrix, you wouldn't be able to look at it immediately, but then you could get your criterion for whether those things are positive, definite, or not. Okay, it would remind you of solutions to quadratic equations. Right? It's related. So that's the critical points. Maybe we'll put down one more interesting function just to see here. we could make one up and put it on a homework. So here's an example. F of x1 and x2 equals x e to the minus x squared plus y squared yeah, this is good. We want to stay with things that we can just graph. So x e to the minus x squared plus y squared and x1, and let's call that x2. x1 squared plus x2 squared. Yeah. Okay, so that would be, without the x in front of it, would be a Gaussian type of thing in 2 space. In 3 space, it would be a mountain, a Gaussian mountain right around the origin. If you multiply it by x, though, what's going to happen? And we could also try to multiply it by x1. And you're going to get first of all, consider, I'll use another letter, g of x equals x e to the minus x squared. What does that look like? For positive x, x e to the minus x squared is going to do something like that. And for negative x, it'll do something like that. So it's got a local maximum, it's got a local minimum. Now if you do this in more than one dimension, it's just going to become richer, more complicated. At some point you're not going to see exactly what's going on. But your analysis, of course, will take you there. Okay, good. And, and in fact, these kind of things are great for, I think we even did one of these with a minus sign in front of it last semester because we wanted a potential well, right? So those are good. Okay. This is for visualizing. And yeah, so this diagonal example is good enough. Okay, let's go back to small oscillations now. We had a couple of examples of small oscillations to remind us what they were. In one dimension, we had the frictionless, mass on a frictionless curve, x, y. We had a curve y is equal to f of x. We had a local minimum here. We had found our Lagrangian to look like this: 1/2 m1 plus f prime of x squared x dot squared minus mg f of x. So this is an excellent example. If you were to write out the Euler-Lagrange equations for this expression, they're going to be very complicated and nonlinear. If we linearize the whole thing around x0, we're just going to be in our potential well, quadratic potential well, the way we were before, the way we did last semester. Yeah, just to remind you, we had said this was an example of 1/2 A of Q dot squared minus U of Q. Right? So that was the most general 1 degree of freedom Lagrangian. And we saw this was an example that's going to have a small oscillations problem built in. So for higher dimensions, we have this problem with the mass, spring K, and L theta, right? We had this example, and this was going to have 2 degrees of freedom. We had X, L is L of X theta, X dot theta dot. And this was of the type L is equal to 1/2 double sum ij aij of q qi dot qj dot minus u of q1 to qn. So that was that was of that type, or q1 and q2 were x and theta. And again, this Lagrangian was pretty involved. The small oscillations of this one, however, are going to be a lot simpler. And I just want to add to this discussion here, in keeping with what we had said above here, where's the equilibrium? Okay. We can find it by construction. It's going to be, say, when we can take x equals 0, we can declare some equilibrium point. Well, actually, when that spring is unstretched or uncompressed, so x equals 0 and theta equals 0. And so we'll find when we construct the potential energy around that, it's going to naturally be a local minimum. We're not going to have to do any determinant tests or anything. Good, so there's an example. And I'm going to go through with the full-on derivation. There's a number of more examples. Let's see how we're doing here. Yeah, in particular, this is our Lagrangian. We had arrived at this one right here. We did a detour because we wanted to learn about Taylor expansions and n variables. Okay. Now we're back to this Lagrangian, and we're going to do with this Lagrangian what we had discussed over here. Okay. In fact, this is perfect. I have this on the board. So here, in fact, I'm going to call, and I'm referring to this one right here, I'm going to call A of Q is this M1 plus F prime X squared, my A of Q. M, now I'm making the mistake of using the same letter twice. I could call it capital M. M is going to be A Q0 is equal to M1 plus F prime of X0 squared. But this, of course, is 0. So it's just n. And what about u of q? Expand to second order. Expand to second order about x0. gonna save this for an exam, but we're so far into it, let's just go ahead and do this one here. So that small oscillations Lagrangian, L sub small oscillations turns into 1/2 M. I'm just gonna call it x dot squared plus 1/2 kx squared. My previous x0 minus x, I just rename x. Okay. My m I just defined up there, and my k is mg f double prime of x0. So exactly what we did last semester. And my point is, I started with this complicated thing here, and I turned it formally, and I'm calling it small oscillation, formally right into this thing here. And once we see this, by the way, it's a minus sign. Once we see this, we're done. Okay, in the one variable problem. Now we have to do the same thing with this guy here, and once we see it, we're not going to be done, but we'll be partway done. Okay, so this one, this example up here from top to bottom, go ahead and study this one. It's an important one. And yeah, we have that. So let me see how much time we have for this. Yeah, we'll do this. We'll do this part way. Good. So now we're talking about this Lagrangian up here, the one in the blue box, and we want to construct the small oscillations Lagrangian. So for small oscillations, we have Q sub 0 is a critical point. It's a local minimum of our potential energy. Okay, that's the first thing. Then we're going to define x sub I is equal to q sub I minus q0 sub I. So these are generalized coordinates. We're going to turn this into name x, qi minus q0i. And we're going to define m sub ij equals a sub ij evaluated at q sub 0. In honor of the mass. They're not masses, but we're going to get something that looks exactly like that right there. So m sub ij, aij of q sub 0. Really an n variable, what we did right up there. And actually we should note for this, x I dot is equal to q I dot because that's a constant. Okay, so x I dot is equal to q I dot. And anything else? Expand u of q in a Taylor series it's going to be u of q equals u of q0. Your first order terms are going to vanish because q0 is a critical point, and your next one is going to be this 1/2 sum of d squared u qi qj of q0 qi minus q0i. Good, just fit qj minus q0j. You're going to have those quadratic terms right there. So we're going to give these a name as well. I'm going to erase this now. So from this expansion, the constant here doesn't matter, and we just have to give these things a name. So we're going to name Kij is going to be this d squared u dqi dqj evaluated at q0. And so now everything is ready. We take this Lagrangian and turn it into the small oscillations Lagrangian. Now, L small oscillations is 1/2 sum over ij mij xi dot xj dot minus 1/2 sum over ij kij xi xj. So we have two quadratic forms of the kind we just studied. Okay. And here I'll put a box around this. Just can't keep everything at the board at the same time, but here's the first thing to notice when you write this out. So write this out, make it as clear as you can, and you'll notice when n equals 1, okay, we'll even write I equals 1 to n, j equals 1 to n. 1 to n. 1 to n. That's j. When n equals 1, this is just the harmonic oscillator. So when n equals 1, you just have 1/2 mx dot squared minus 1/2 kx squared. X dot. So you're justified, after we've studied this, you'll be justified in looking at this and seeing this easy one here, okay? But we haven't done the analysis yet, but you just see the form now. Instead of m being a parameter, we've got an entire matrix. Same thing for k, we now have a matrix. But we know that both of these matrices are positive definite. Okay, they're n by n collections of constants. Positive definite matrices, and we're going to end up with a process that takes us, just as this thing turns into x equals a cos omega t plus phi, right? We're going to find a process that allows us to find out what this x1 to xn is. So that's one of the few theories that you can take it through to completion for the entire class of problems. The entire class of small oscillation problems will be solved. And we've made it to this small oscillations Lagrangian. That's a good place to, maybe a good place to declare victory. Let's see here. We can go a little bit beyond. So here's what we're going to do next. We have now found the small oscillations Lagrangian. We now find the Euler-Lagrange equations for it. And that's as far as we'll get today. So we'll do that. So what's really important is we're only going to have to do it once, because we start with a problem, we analyze it, we get all these definitions here, and we now take the Euler-Lagrange equations. So Euler-Lagrange equations. dt partial L small oscillations partial x of k dot. Okay. I was going to choose another subscript, another index, minus dl small oscillations dx of k is equal to 0. We're just going to do this one, and then we're going to inherit everything else. So here we go. dl small oscillations dx of k is equal to, we've got a minus, in fact, minus this, so get rid of that, we got the plus sign, we've got the 1/2 ij kij. Using the letter k twice, but that's just the way it goes. So this is a calculation we've actually done before. So we have d dx of k of xi xj. We did this on our energy conservation discussion here. So we've got a 1/2, we've got a double sum. In fact, I'm going to do this since we've done this before. Sum over I, we're going to get rid of this second sum because right here we're going to have the derivative with respect to x sub j. Okay, well, I'm not going to skip the step after all. Let's do this. J, K, I, J. We'll do it with the Kronecker delta is the way we've been doing it. So we have hold x sub I constant, and then the derivative with respect to x sub j is Kronecker delta kj, hold x sub j constant, and we have derivative with respect to x sub I is Kronecker delta ki. Okay. This is good to practice. Now, we're summing over the j matrix, and only when j is equal to k, the j sum, when j is equal to k, do we have a non-zero contribution. We have a 1/2 sum over I, k, I, k, xi, and then for the other one we have a 1/2 sum over j, and now only when I is equal to k do we have another contribution. So we have k, kj, x sub j. And now we're going to again assume kij is symmetric. Same thing holds as with our earlier discussion. We can make it so when we're doing the construction. I'll show you that later. So if kij is symmetric, then these two sums are actually the same. And we end up with equals sum over j, k sub k, k sub kj, xj. Now this one we're going to get for free because we're doing the partials with respect to xk dot, okay, xk dot, so we actually have over here d dt sum over j a kj xj dot is exactly the same form as this. Of course, that time derivative is going to go through, by the way, this is m, wasn't it? M kj. Yeah. M kj xj dot. Give us x double dot. We're going to add this to it, and I'll put it right there. What we end up with is the sum m kj xj dot plus k kj xj is equal to 0. And you know what? Let's go ahead and use I instead of K now that we're done. J equals 1 to N. I will leave this for now. So these are our Euler-Lagrange equations. I'm going to start with this next time. Second derivative. But again, just look at it when n equals 1 and it's just your harmonic oscillator. Now we have a system of coupled equations. In the limit of 1 degree of freedom, it's just the harmonic oscillator. Okay, it's going to be a great progression of ideas here. Let's see where we're at. Good, this is a good place to stop. We derived the Euler-Lagrange equation. I'll start with this again next time, say a little more about it. But for now, we see it is, this is what I'll end with, n equals 1. Then we're looking at mx second derivative plus kx equals 0. This is what we studied so much last semester. Okay, so here, if we see this, we can declare victory. This we're going to have to learn about the general solution theory. Okay, good. That's it. We'll see you guys next time.